It works fine, yeah. The green light has to be on.
Yeah. Okay.
But I can yell.
Want to use this or you want to?
I'll use that. Yeah.
Thanks everyone for coming to the UTIG seminar on Friday morning here. Today as a guest, we have Collin Brandl. Collin Brandl grew up in upstate New York, and then for his college degree decided to venture out in the rest of the US and went to Texas A&M for his undergraduate, where he worked with Bobby Reese, who's of course a former grad student here at UTIG. Then so he became interested in marine geophysics early on. Then later he did a master's degree and a PhD at the University of New Mexico with another UTIG alum, which is Lindsay Worthington. And for his master's and PhD, he worked at the rifting margin of the mid-Atlantic states of the US, the so-called ENM data set, but then also worked on the structure of the Pacific Northwest convergent margin, and it's in relation to seismic hazard. And since then, he's been a postdoc at Lamont for about a year, working with Anne Bissell and also with Nathan and I on a project on Blake Plateau. But this morning, he's going to talk about the Queen Charlotte plate boundary, more in its larger plate tectonic evolution. So please welcome Collin Brandl.
Okay. Hello, everyone. Yes, thank you for having me. I really appreciate this opportunity to come by and share some of the work I did during my dissertation, looking at sort of the overall structure and behavior of the Queen Charlotte plate boundary. Before we get started, I just want to acknowledge my quite a large group of collaborators from a bunch of places, including in the U.S. and in Canada, when we're all sort of combined by our interest of better understanding this plate boundary that's relatively unexplored. So in this talk, it'll be sort of two parts. The first part will be looking at some crustal scale imaging of the plate boundary to answer a bunch of questions about ultimately how oblique convergence is accommodated by this transform system. And if the title wasn't provocative enough, maybe pointing to this region being a site of incipient subduction. And then in the second part, we'll be doing some derivative analysis of the seismic data, looking at bottom simulating reflectors to better understand the... Oh yeah, for sure. Sorry, technical difficulties. We struggled with this earlier. So as you'll see here, this is the room we're in, and I think it said screen sharing stop too. So okay, let me just fuddle with this for a second. Okay, hopefully we're all good. Yeah, so in the second part, we'll be looking at some bottom simulating reflectors to understand the thermal structure of the plate boundary. It's a little bit more derivative work. I promise I'm pushing advanced slide and it's not working. But I think this computer really does not like my PowerPoint because I have a lot of high-res images. Right? Okay, we'll just do it down there. So I struggle to think about or to figure out the best way to sort of introduce this work sometimes, right? Queen Charlotte, if you're not familiar, is a transform plate boundary. So I think the most logical way is to start with transforms. But as the title suggested, ultimately we're getting to subduction initiation. So maybe that's the best place to start. I also find that a lot of people don't really know where Queen Charlotte is or have maybe never heard of it. But for now, at least, I think starting with transforms is the best. So transform plate boundaries represent about a third of the total plate boundary system. And while they can rupture in really large earthquakes and they can impact populations nearby, I think sometimes people or scientists maybe overlook them or just assume that they have this simple strike slip deformation. when in reality, they can be quite complex. They can accommodate a lot of oblique motion, and they can have really cool, interesting crustal structure. Now, many of the high impact transform plate boundaries are found onshore, and in these examples I'm showing here of San Andreas or the Anatolian faults or the Alpine fault, they all could, with a large earthquake, could really impact these nearby populations. But while it's really easy to go out onshore and see what the surface faults look like and physically study the plate boundary, because they're onshore, it can be sometimes tough to really understand the full crustal scale picture of what's going on. There we go. Transforms have also been maybe recently recognized for their potential of subduction initiation, where at a pre-existing transform plate boundary, in this simple little cartoon that experiences some sort of convergence, you could potentially form a new subduction zone. And subduction initiation is this sort of outstanding question of plate tectonics. We know subduction is very important, but we don't really know, maybe to the best extent, how they form. Transforms are maybe an ideal location because they have a pre-existing weak zone, in this case, this transform plate boundary. They often have quite significant lithospheric contrasts in density, in temperature, in thickness. And as I mentioned, they often accommodate some oblique motion. And as subduction zones are convergent margins, having some sort of convergence is sort of a prerequisite. Transforms have been recognized through modeling as this, or oblique transforms have been recognized as modeling as one of the most ideal locations. So in this model, we have a pre-existing transform boundary that's experiencing only strike slip. As you would expect, there's probably no subduction initiation with just strike slip motion. But with that same plate boundary, if you only had convergence, subduction initiation might fail because there was too much intraplate deformation. Whereas if you have oblique motion, as you would experience at a transform, subduction initiation is able to propagate. And this has been observed on Earth. One of the best examples is Pusagar Trench, southwest of New Zealand, which started as a pre-existing transform, and over the last 20 million years has evolved to be an active subduction zone. So this whole study will be focused on, or all this talk will be focused on the Queen Charlotte plate boundary, which is highlighted by this yellow line in the map. It's the Pacific North American transform plate boundary offshore of Western British Columbia and Southeast Alaska. It effectively connects Cascadian subduction to Alaskan subduction, and many people have considered it to be an underwater analog of San Andreas, right? They're both the Pacific North American transform plate boundary. They both separate ocean continent, an oceanic plate from a continental plate. Queen Charlotte is really unique. It's the fastest slipping ocean continent transform on Earth with a relative motion of about 55 millimeters per year. And most of that motion is localized to a single fault strand, the Queen Charlotte fault, which you may have heard the plate boundary be referred to as, because it accommodates most of that relative motion. This is some multi-beam bathymetry of the Queen Charlotte fault in the northern segment of the plate boundary. And you can see just how highly localized it is despite being such a fast slip rate transform plate boundary. Queen Charlotte has a history of large earthquakes. There have been 7 magnitude 7+ in the last century, including Canada's largest recorded earthquake, which was this magnitude 8.1 strike slip event in 1949. And a very unique event that I'm fond of. In 2012, there was a magnitude 7.8 thrust earthquake, which I know on a transform boundary, very unexpected. Oops. So the Queen Charlotte has this curvilinear strike, as you can see just by the simple yellow line. So as you move from north to south, the obliquity between the Pacific plate motion and the plate boundary increases from about 0 degrees in the north to about 25 degrees in the south. And this translates to between 0 and 25 millimeters per year of oblique convergence that must be accommodated by the system somehow. So in that region with the highest convergence this is offshore of Haida Gwaii, British Columbia, which was the very nice picture on my intro slide. And west of the Queen Charlotte fault in this region, we have what's this feature called the Queen Charlotte Terrace, which was first recognized bathymetrically and since has been considered part of the response or the accommodation of oblique convergence by the system. And this Queen Charlotte Terrace and this oblique convergence has resulted in decades of debate over how it's accommodated. There's two end-member sort of hypotheses. The first is crustal thickening, where you would have the Pacific plate colliding with a much thicker North America and internally deforming, inverting oceanic crust and sediments, and that would form the Queen Charlotte Terrace. Alternatively, you have underthrusting, or if you ask some people, subduction, where you would have the Pacific plate underthrusting the Queen Charlotte Terrace and maybe North America, and the Queen Charlotte Terrace would be forming more like an accretionary prism. Related to this uncertainty in the accommodation mechanism is also the occurrence of strain partitioning. So under oblique convergence, there's two potential mechanisms that could be accommodating that. You might have distributed strain with many strands of oblique faults that are accommodating both the strike slip motion and the convergent motion, or you could have partition strain, which would have one strike slip fault accommodating strike slip and maybe many thrust faults that are accommodating the convergence. This behavior has a big impact on the seismic hazard of the region, as it sort of decides how slip is distributed throughout the system. Now, I mentioned that earthquake in 2012. This is this magnitude 7.8 Haida Gwaii earthquake. And as I said, it was a thrust mechanism occurring on a primarily transformed plate boundary. It also generated a small tsunami. I think the local run-up was up to 12 meters, but the far field wave height was, I think, 30 centimeters in Hawaii. So not giant, but still quite a significant tsunami in an unexpected place. And this earthquake, there's a lot of uncertainty in the slip distribution of the earthquake because this region is very remote. It's it has a lack of instrumentation, and there's a lot of uncertainty in what the surface of the fault that actually ruptured this earthquake is. So this is sort of a summary paper of a bunch of different earthquake models for that 2012 event. And you can see that slip ranges from being entirely beneath Haida Gwaii to almost entirely beneath the Queen Charlotte Terrace on the Pacific plate. The faults are parameterized in a variety of ways, and each of these source models equally well explains the 2012 earthquake. Regardless, this event occurred on a fault that's sort of a hypothetical fault at this stage called the Haida Gwaii thrust, which would represent this sort of plate boundary thrust fault, assuming the system is oblique convergence accommodated by underthrusting. So this earthquake was one significant data point that pointed towards underthrusting and strain partitioning, but it's only one data point, and there's a lot of uncertainty with its use. A lot of that uncertainty results from the previous imaging of this region. So I'm showing some examples here. On the left, we have some single channel data, single channel seismic data that was acquired in 2013 as part of a site survey to deploy these OBSs after the earthquake. And you can see that the seismic data effectively images the near seafloor structures, the shallow subsurface, but that's about it. There is a plethora of single channel paper records that also do the same thing. They image the shallow subsurface, but really the internal structure of the Queen Charlotte Terrace and this potential of a Haida Gwaii thrust is very uncertain. There's been some sparse receiver function analysis on Haida Gwaii that have found a low velocity zone beneath the islands that they attribute to a slab, again, pointing towards underthrusting, but this is really the best indication that anyone's had, along with the earthquake, that underthrusting might be accommodating the convergence here. So to address some of these questions and to sort of illuminate the real crustal structure of the plate boundary, in 2021, we had an experiment called Transform Obliquely on the Queen Charlotte Fault and Earthquake Study, which we affectionately refer to as TOOCS, like the hat, which was inspired by the sailors on the Canadian vessel, as they all wore toques every single day consistently. So we collected, along with some active source OBS data, we collected 4,200 kilometers of multi-channel seismic reflection data along the plate boundary, which is all of these thin gray lines. And for this part of the talk, we'll be just focusing on a select few profiles offshore of Haida Gwaii. So we'll look at these 5 profiles, and we're going to be using the structure we see on these profiles to answer a bunch of science questions, some that I already mentioned, like how is oblique convergence accommodated, trying to understand strain partitioning, understanding the nature of the Haida Gwaii thrust, but then also looking at the evolution of the southern part of the plate boundary and trying to classify or trying to understand potentially subduction initiation here. So we're going to step through some of the profiles just to look at some of the structures. We'll be looking at first these 4 strike perpendicular pre-stack time migrated profiles. They're oriented from south to north. So this is the southernmost profile, QCF 16. This is the northernmost profile. We'll be able to get this sort of regular sampling of the internal structure of the Queen Charlotte Terrace. And these profiles image not only the Queen Charlotte Terrace, which is this uplifted shallow feature here, but also the incoming Pacific plate, the Queen Charlotte Fault itself, and then a little bit of the continental shelf. It's not the focus of the talk, but this is nice, relatively new data. I think it's good to sort of highlight some of the things we're seeing adjacent to the Queen Charlotte Terrace. So on the Pacific plate, we see that we have this east-dipping oceanic crust. There's extensive normal faulting in the sediments, and we maybe have some sporadic places where there is intraplate magmatism from the Bowie hotspot, which is something I'm actively working on right now. In the past, this normal faulting was documented in some of the legacy data, and it was attributed to the downwarping of the plate linked to the onset of underthrusting. The faulting extends through most of the sediments, but not into the trench fill. And then moving to what we're maybe most interested in, the Queen Charlotte Terrace's structure. Oh, sorry. If we just zoom in onto it, so this is the Queen Charlotte Terrace with all of these thrust faults. And if we just sort of step through some of the major observations we see near the deformation front within the outer maybe 10 kilometers of the terrace, we have a series of active thin-skinned thrust faults that are accommodating the convergence, and they're uplifting Pacific plate sediments to sort of build out the Queen Charlotte Terrace. Moving landward a little bit, we have some probably inactive thin-skin thrust faults that were at some point responsible for some accretion, but don't seem to be actively deforming at this right now. All of these thin-skin thrusts branch off of this interpreted décollement, which tops underthrusting oceanic crust and sediments. So this black dotted line is a continuation of the top of oceanic crust we saw on the Pacific plate. And this blue dotted line is our interpreted décollement. So all of this, everything below the black dotted line would be underthrusting oceanic crust, and everything between the blue and the black would be underthrusting sediment. And then very close to the Queen Charlotte Fault, we see a series of probably inactive strike slip faults that don't seem to be accommodating any motion now, but maybe represent some earlier stage of deformation in the system. And then if we step towards the Queen Charlotte Fault itself and the Haida Gwaii Shelf, the Queen Charlotte Fault, which is the reminder, is really the primary plate boundary structure for most of Queen Charlotte. It accommodates up to 55 millimeters per year of motion. It's this near vertical, it seems that the only accommodating strike slip, and it's very localized in the shallow subsurface. We see this transparent zone on either side of the fault that we're sort of interpreting as the damage zone, and it ranges in width from 200 to 800 meters. So very localized, as we saw in the bathymetry in the northern segment at the seafloor. If we look at the shelf structure, the Haida Gwaii Shelf is much less deformed than the Queen Charlotte Terrace is. And this is sort of pointing to the Queen Charlotte Fault, or the Haida Gwaii Shelf is maybe acting as a backstop for the deformation that's occurring within the Queen Charlotte Terrace. So trying to get to some of the questions we're thinking about, the first being, how is oblique convergence accommodated by this system? So as we saw, the Queen Charlotte Terrace is mostly built from these thin-skinned thrust faults that are inverting oceanic sediments, either at some time in the past or actively. which means that these thrust faults are what is actively accommodating the convergent motion along with the underthrusting of the Pacific plate. So what this crustal structure is showing us is that the hypothesis by Roy Hinman throughout his life of underthrusting was probably the correct hypothesis, and that we see very little evidence of there being any internal deformation of the Pacific plate that would suggest it's colliding with North America somewhere at depth. We also see that strike slip motion is actively being accommodated mostly by the Queen Charlotte fault. These older strike slip faults maybe represent that earlier stage of deformation, but most of the strike slip motion is actively accommodated by just the Queen Charlotte fault. And that suggests that strain is being partitioned between the Queen Charlotte fault and the Queen Charlotte Terrace. So all of the thrust faults are accommodating the convergence. Queen Charlotte fault is accommodating strike slip. Now we see some evidence that the strain partitioning probably deviates from like the pure orthogonal case, as some of these frontal thrusts have quite complicated or complex geometries that sort of lead us to think that maybe there's some oblique motion being accommodated out here, which is not unheard of. That's something that's seen at in models of crustal slivers. But predominantly, strain is being partitioned in the system as underthrusting and thin skin faulting is accommodating the convergence. All right. We started at 10:30, right? I just want to keep myself on track for time. The next question to address is, what is the Haida Gwaii thrust? So as I mentioned, in 2012, we had this thrust earthquake rupture, this hypothetical thrust fault surface. But up until this data set, we had no real images of what that thrust fault might be. So we're interpreting this décollement that all of the thin skin thrust branch from or splay from as the Haida Gwaii thrust, or the shallow portion of the Haida Gwaii thrust. And if we look at this along strike profile that I haven't shown yet, which was acquired right in the center of the Queen Charlotte Terrace, we can identify the Haida Gwaii thrust at depth for about 180 kilometers long strike. So this is a continuous through-going thrust fault beneath the Queen Charlotte Terrace. We see that we interpret the décollement. So what this really suggests is the Haida Gwaii thrust is this sort of, maybe to jump ahead a little bit, the Haida Gwaii thrust is effectively a nascent megathrust that you would see at a modern subduction zone. It's not as big as a megathrust as you might normally think. I don't know a better name for it. A mini megathrust, maybe. But it's a quite extensive fault that exists for almost the entire length of the Queen Charlotte Terrace. If we sort of think about some of the geometry of the Haida Gwaii thrust that we see in our profiles, so these cartoons are based on the seismic data that's been converted to depth with a very smooth velocity model. The Haida Gwaii thrust dips to the east at anywhere between 9 and 13 degrees. In past models of the 2012 earthquake, they all assume that the fault dips at about 15 to 25 degrees. So this shallow portion of the Haida Gwaii thrust is much gentler, as a much more gentle dip than the deeper portion of the thrust. What this maybe suggests is that the 2012 earthquake did in fact rupture further down dip, or with some of the uncertainties in the source models, that it could have ruptured shallower just with a gentler dip. And with our sort of confirmation that the Haida Gwaii thrust is this extensive through-going plate boundary scale thrust, this sort of verifies that larger hypothetical earthquakes like magnitude 8 pluses are possible here. In this study that sort of summarized all of the previous earthquake models, they explored some hypothetical potential larger scenarios. And just with very simple assumptions about what the Haida Gwaii thrust looked like, maybe following the length of Haida Gwaii, they were able to reasonably generate in magnitude 8.3, I believe. But with a real geometry, this potentially could increase even more. So moving towards the future, the Haida Gwaii thrust might be a quite significant mini megathrust earthquake risk. And sort of the culmination of most of this imaging is a better understanding of the tectonic framework of the Queen Charlotte Terrace. So with our depth profile, our depth converted profiles and these conceptual or interpretive cross sections, really the Queen Charlotte Terrace is built out of mostly accreted sediments. There's some slope sedimentation. There might be some places that have some duplexing, whether it's sediments or oceanic crust. But predominantly inverted oceanic sediments build the terrace out. The Queen Charlotte Terrace is bounded by this Haida Gwaii thrust, so a plate boundary scale thrust fault, and then the Queen Charlotte fault, or this sort of this strike slip fault. And what that means is the southern segment of the plate boundary is much more analogous to the crustal slivers that we see at oblique subduction zones than to other transform boundaries. So in this is a very simple cartoon that's based on Sumatra, which has a accretionary prism sliver bounded by the Great Sumatra Fault and the trench. This is an example from the Lesser Antilles with the Bunce Fault accommodating strike slip motion, and then you have a accretionary prism accommodating all of the convergence. And then, as I mentioned at the start with subduction initiation, Pusiger Trench is a similar crustal structure where you have the crustal sliver bounded by a strike slip fault and then the plate boundary thrust. So when we're thinking about Queen Charlotte moving in the future, or as you are thinking about maybe future hazard models of the plate boundary, it's very important that you consider that this region appears more like a sliver or acts more like a sliver or is a sliver than a primarily transform only plate boundary. Another interesting observation we've made is there seems to be an evolution in the deformation that occurred within the Queen Charlotte Terrace. So as I noted, closer to the Queen Charlotte Fault, we see that there are these series of inactive strike slip faults. And those probably represent some earlier deformation where maybe the system was more distributed, maybe strike slip was more distributed across multiple fault strands, but has now progressively localized to just the Queen Charlotte Fault. Moving seaward from those strike slips, we see that there's these inactive, probably thin-skin thrusts that at some point were accommodating motion and inverting sediments, but aren't anymore. And then obviously, wrong direction. Sorry, PowerPoint. Oh, there we go. Okay, and then at the deformation front, we have these active thrust faults. So moving from PowerPoint really does not like my, this computer does not like my PowerPoint, jeez. Okay, so we see that there is this progressive evolution where near the Queen Charlotte, I promise I'm not pushing buttons. Near the Queen Charlotte Fault, we see these older strike slip faults. So some earlier stage of deformation. That progresses into these thin skin thrusts and then actives. So we see this clear evolution in the deformation. What we think that means is that there was a progressive evolution in the crustal structure of the Queen Charlotte Terrace. Starting with this period of, eventually we'll get to a cartoon, I promise, that highlights this, if I can figure out how to push the buttons in the right way. Okay. So what we think was about 20 million years ago, after the Yakutat terrain translated past Haida Gwaii, it uplifted Haida Gwaii some. At this stage, we probably had some maybe thick-skinned crustal deformation, or maybe we just had this distributed strike slip. But regardless, this early faulting it was a much more, there was no strain partitioning, and there was much more distributed deformation. At some point in the system's history, that deformation transitioned from this distributed strain to partition strain with thin skin thrusting and strike slip being accommodated only by the Queen Charlotte Fault. This sort of behavior has been observed in analog models of transpression, where starting with a very simple transform pre-existing weak zone, early deformation has these sort of near vertical, more like one-sided flower structure looking faults. And as the system accumulates shortening, eventually it transitions to being thin-skinned, and then strain partitioning is sort of enabled by this progressive evolution. So from that, getting into maybe the provocative part of the title, or subduction initiation, or is this place a new subduction zone? As I mentioned at the start, transforms are this ideal location to initiate subduction. Modeling suggests that oblique motion might be critical for it, and we've seen in real life on Earth that transforms can very efficiently be converted to subduction zones, with Pusiger as sort of the best example. Pusiger right now has this oblique subduction with a crustal sliver that's bounded by a strike slip fault and a plate boundary thrust. So if we think about what the structure of the Queen Charlotte Terrace looks like, where we have a crustal sliver bounded by a plate boundary thrust fault and a strike slip sliver fault, Queen Charlotte is much more analogous to a crustal sliver. And combined with some of the other evidence I mentioned, like this low velocity zone interpreted from receiver functions, or some seismicity, we suggest that Queen Charlotte is, in fact, an incipient subduction zone that occurred at an ocean-continent transform boundary, with a very similar history to Pusiger Trench. Now, unlike Pusiger, Queen Charlotte has not technically achieved subduction. So in this sort of simple schematic of subduction initiation, Pusiger is in this achieved or maybe nearly self-sustained state. Queen Charlotte is probably somewhere between incipient, where the system has evolved to having localized deformation, but we haven't yet reached a stage of arc volcanism or a Benioff zone, which is sort of characteristic by definition of what achieved subduction is. But you can consider these two environments to be very analogous, and maybe Queen Charlotte represents a sort of earlier stage of what Pusiger could have looked like. Is a little bit less mature through the subduction initiation process. So to sort of wrap up the first part of this talk, we see that the Queen Charlotte Terrace is this strain partitioned crustal sliver with bounded by a plate boundary scale thrust fault and a strike slip sliver fault. It's really more analogous to oblique subduction zones than it is to other major transforms. And that oblique convergence is accommodated by thrust faulting, by under thrusting, and slip on the Queen Charlotte fault in this sort of strain partition behavior. We see that the Haida Gwaii thrust is this through-going plate boundary scale thrust fault for at least 100, and this says 70, but it's at least 180 kilometers long strike. And that means that it could represent a much more significant earthquake hazard and tsunami hazard in the Northeast Pacific that I think has been under-examined in hazard models. But hopefully moving forward, we'll be able to do a better job of considering future events on this fault and the destruction that they could lead to. And then the third big takeaway is the Queen Charlotte Terrace has evolved from this distributed oblique slip to strain partitioning. And with this crustal sliver and strain partition deformation and all the other evidence we have, we argue that Queen Charlotte is a site of incipient subduction. It's at an earlier stage than many other incipient subduction zones at transforms, but nonetheless maybe represents this sort of early state of deformation as the system is evolving from localized deformation to achieved subduction. And then moving into part two. So now that we know sort of what Queen Charlotte looks like, we have this tectonic framework, and we have as I said, a nascent megathrust. Another part of my dissertation was to try to better understand the thermal structure of the plate boundary using bottom simulating reflectors. So the thermal structure of the lithosphere of a plate boundary system influences deformation and seismogenesis, and this is sort of shown by this little simple cartoon here from Collin Brandl, where depending on whether you're on the Haida Gwaii thrust, when the shallow Haida Gwaii thrust, the deep Haida Gwaii thrust, or the Queen Charlotte fault, how each is behaving in terms of their slip behavior. This is controlled by the temperature. Similarly, seismogenesis of the Haida Gwaii thrust is also partially controlled by the temperature of the plate boundary. Generally, we think of the seismogenic zone extending to 350 or 400 degrees C. And this has been somewhat quantified with some of the previous thermal modeling of the region, assuming that the Haida Gwaii thrust is this very, very basic fault plane, but the deepest extent of the seismogenic zone could maybe reach 20 to 25 kilometers in depth. Now, in those models I mentioned of the 2012 earthquake, they all sort of assume a very simple, flat, homogeneous fault surface that dips from 15 to 20 degrees and generally extends to about 35 kilometers of depth. But knowing that this plate boundary is so variable along strike and there's so much differences in the deformation style, it's very likely that this is not the simplest case. So to better understand the thermal state of the plate boundary, I looked at bottom simulating reflectors. And for those who may be unaware, bottom simulating reflectors are a reflection that manifests in active source seismic data that corresponds to the base of the gas hydrate stability zone. And using information about the water column temperature, the depth of the BSR, you're able to extract what the shallow geotherm is. This method in active source seismic data is advantageous because it's got a high sampling density with very spatially extensive measurements compared to maybe the more standard heat flow probe, which is limited to a maybe very near seafloor and really only measures one specific point. There have been some previous constraints on the thermal state of the Queen Charlotte. This is from 1982. This is a heat flow study that examined, that did some physical probing of the southernmost part offshore Haida Gwaii. And using that heat flow probe data, there have been multiple thermal models that have found there's this very rapid decrease in heat flow near the trench or near the deformation front of the Queen Charlotte Terrace. And they've used these models to sort of constrain the hypothetical temperatures of the Haida Gwaii thrust. There has also been a study using BSRs in legacy seismic data along the plate boundary. So this is from 2020. They examined paper records and some data from the Canadian seismic database. And all of these colored dots represent BSRs that were interpreted sort of intermittently along the Queen Charlotte Terrace. Their biggest takeaway was they found that there was a long strike, a very small long strike decrease moving from south to north, which they attributed to the age of the Pacific plate, suggesting that the age of the Pacific crust was maybe the primary control on the temperature of the plate boundary structure, which therefore would influence seismogenesis and plate boundary deformation. So for anyone who's unfamiliar, this is what a BSR looks like in active source seismic data. Generally, it's this cross-cutting, very bright negative polarity reflection that follows the seafloor, but doesn't occur at typical times you'd expect for a multiple. And with our new seismic imaging data, not only do we have more observations along the plate boundary at a sort of a more regularly sampled interval, we also are able to provide direct structural context to these measurements, which the legacy BSR study was not able to. So we identified BSRs on 18 of the 23 profiles. So that's all the red dots on here. And these BSR observations really significantly supplement the legacy observations, which are all the black diamonds. BSRs are really prevalent in the Queen Charlotte Terrace or in the southern half of the study area. And they're very sparse in the northern half with only a handful of very isolated observations. So to go from BSRs to thermal gradient, you just have to take some assumption of the water column temperature, which in this case we use the XBT measurements from the active source cruise. And you, using the XBT water column temperatures and a model of the hydrate stability curve, and then the seafloor depth and the BSR depth from the seismic data, you're able to convert or to calculate the shallow thermal gradient. Now, typically, people discuss, when they think about temperature, they think about heat flow, which is which you can calculate by taking the thermal gradient and multiplying it by a thermal conductivity. Nailing down the thermal conductivity in this area is a little bit tough. There are no real drill holes that would be able to tell you the physical properties of the sediments. And the legacy study with BSRs just assumed they only looked at thermal gradient because thermal conductivity was too difficult to nail down. So following that, we'll only really be looking at thermal gradient. Or if you really want to think about it, we're looking at thermal gradient and just assuming that thermal conductivity is equal to 1, whatever is easier. So with our BSR observations, we're most interested in looking at some of the relative trends that we see in the calculated thermal gradients. So this plot is of thermal gradient versus distance along the QCF. So this is the southern edge, this is the northern edge. All of the red and the black dots are BSR observations with their associated thermal gradient. The biggest takeaway here is when you project the BSRs along strike, we see this pretty significant decrease from about 90 degrees C per kilometer to about 50, moving south to north. And then we see this sort of increase moving into the northern section of the fault. Now, as I mentioned, the legacy study using the legacy seismic data, it would have just been these black dots, and they were able to sort of partially capture this trend. But with the new data from TUCS, we really sort of fully illuminate what this trend actually looks like. Now, if we look at the strike perpendicular thermal gradients, so now we're oriented perpendicular to the plate boundary, we see that there's this rapid landward decrease of the thermal gradients near the deformation front. Within 10 kilometers of the deformation front, the thermal gradients decrease from about 100 degrees C per kilometer to near 50 before they sort of plateau and then gradually increase to about 80 degrees C, approaching the Queen Charlotte Fault. Now, and I mentioned at the start that there was this quite significant difference in the distribution of BSRs along the plate boundary, where we have significantly more in the southern part of the study area than we do in the north. Now, one might assume that this has something to do with maybe major controls on the gas hydrate system that would have that could have an impact. So we examined the deformation front, the feather edge of gas hydrate stability, and the Queen Charlotte Fault, and sort of looked at the BSRs relative to these major structural controls in the system. And it seems like none of those structural controls really have a major control on BSR distribution. There's nowhere that these would effectively limit the BSRs to form along the plate boundary. So it doesn't seem like those have an impact. The biggest difference we see between the southern half of the study area and the northern half is the convergence rate, or the obliquity. As you can sort of tell by the curvature of the plate boundary here, right about the center where we see this transition in BSRs represents this sort of inflection point. We have much less convergence in the northern section. So it's been suggested that less compressional deformation in the northern part of the plate boundary would lead to less gas advection and then therefore less BSRs in the study area, as we really only see the BSRs in the northern part of the section, the northern portion of the study area on these like isolated thrust faults. They're not as widespread as in the Queen Charlotte Terrace. So if we compare our thermal gradient observations to some of these past studies, as I mentioned, the legacy study found this along strike south to north decrease, and this plot is oriented opposite to ours. They found that there was this trend and they attributed it to the age of the Pacific plate. So if we take a similar model for the heat flow of an oceanic plate as it ages, which is this black line here, it grossly overestimates the thermal gradients. But if we modify this curve a little bit and just change the coefficient, so we're still related to the inverse square or the inverse square root of plate age, we're able to really well fit the observed decrease in thermal gradients moving south to north, which suggests that the age of the Pacific plate is the primary control on the thermal state, or the variability of the thermal state along strike. Now, this doesn't explain the magnitudes we see, just that we or find a mechanism to explain this trend. The other comparison to make in the strike perpendicular direction is to the previous thermal models of the plate boundary. As I mentioned, this thermal model from Collin Wang, they used the previously obtained heat flow probe data to sort of model the lithospheric temperatures, and they found this rapid decrease. And their best fitting model assumed that there was vigorous hydrothermal circulation in the oceanic crust and that was what really was responsible for this decrease. Now, we do see a decrease, this rapid decrease at the deformation front of maybe nearly 50% in the thermal gradients. However, by just comparing sort of apples to apples, their heat flow curves or their heat flow curves converted to thermal gradient to our observations, we find that the thermal gradients really don't fit their ideal model, this nu equals 1000 model. We fall somewhere in between vigorous hydrothermal circulation and no hydrothermal circulation. We also find that their models underestimate the BSR thermal gradients moving closer to the Queen Charlotte Fault. So this suggests that the thermal models probably should be reevaluated using all of this data so that hopefully we're able to better constrain the actual the temperature of the lithosphere. As of right now, these are sort of assuming that the lithospheric temperature is very consistent along strike, and we see that these models don't really match what we're observing. And as I mentioned, the biggest implication maybe for this BSR study is that the previous thermal models all assumed a very homogeneous seismogenic zone that reached maybe to 20 or 30 kilometer depths. This seismogenic zone estimate was based purely on that thermal model I just mentioned, and that sort of influenced many of these source models for the 2012 earthquake. However, we've seen that there is a long strike decrease in thermal gradients moving from south to north. So if we assume that that trend in thermal gradients is consistent on the North American side, then we might expect the down dip edge of the seismogenic zone to deepen, moving in that same direction as the lithosphere is getting colder. However, the thermal models also underestimate the values offshore Haida Gwaii. So if we sort of assume that that's consistent beneath Haida Gwaii as well, that would suggest the lithosphere is warmer beneath Haida Gwaii, but that it cools moving to the north. So the down dip edge of the seismogenic zone might be shallower beneath Haida Gwaii, but then progressively deepen to the north. And ultimately, I think this means we really need to reevaluate thermal models of the plate boundary and also the source models of the earthquake so that we can better understand the true hazard potential of this region. And then just to, I guess, wrap it up, but we looked at bottom simulating reflectors along the plate boundary. They're very prevalent in the south, and this distribution variability is likely related to obliquity, where more compressional deformation promotes methane advection. We find a 50% decrease in thermal gradients moving from south to north along the plate boundary, which is primarily controlled by the age of the Pacific plate. Deviations from past models suggest that the Queen Charlotte plate boundary might be warmer and also more variable than previously thought, which could drastically change models of the seismogenic zone. And those should probably be reevaluated so we're better able to accurately constrain the seismic hazard of the region. So with that, thank you very much.
Well, thanks, Collin. Does anybody here have questions for Collin? Go and start with if graduate students have a question about this talk. It's Gamma first.
Great talk. I guess I was interested by this strike parallel line that you took, and how it showed sort of like an undulating décollement, and like why is that?
Well, let me see if I can go back to it without the PowerPoint getting mad at me.
I think it was page like 30.
Learned my lesson of not putting such high-res seismic figures in my PowerPoints like this. Jeez. So the actual seismic reflection image I showed was in time. So partially that's probably from some velocity variability controlling what the time appears. But we do see some of that undulation even in the depth converted image. Again, that might be from velocity variability as we're just using velocities we get during the reflection processing to convert to depth. It might also reflect some real structure, though it would be quite dramatic. So I'm not entirely sure how much of that is real and how much of it is sort of something expected from the velocities there. Yeah, so this is a depth image, or based on the depth converted image. And we do still see some of that variability. This is definitely something I think we should explore more, though, is what the variability of the Haida Gwaii thrust maybe also means for the plate boundary. I didn't mention it, but if you really zoomed in and look at the reflection, the character changes quite dramatically moving along strike. So in some places, the décollement is very bright and the top of the oceanic crust isn't. In some places, it's opposite, where the décollement is very faint and the oceanic crust is very bright, which maybe suggests that there's some variability of those underthrusting sediments. But yeah, definitely something to look at.
Hi, I have a question. So you compared the Pusker subduction zone with your case study area. What are your thoughts on, like, I don't know, like, given that the Pusker is connected to Alpine, which is like a big transform, whereas for this case you're connected to like other subduction zones. Like, would these differences like affect the initiation of the subduction zone that you're thinking of?
That's a good question. I don't know. I guess you're right that Queen Charlotte does connect to the other subduction zones, but I think comparing the Pusiger connected to Alpine is maybe more analogous to the southern Queen Charlotte being connected to the northern Queen Charlotte. I think that ultimately the initiation it transforms, or I think Pusiger has, I don't know if I have a map here, but so the Pusiger, based on the angle of the plate boundary, gets more and more convergent as you move to the north. So it's almost making it easier to initiate subduction, whereas Queen Charlotte seems to be the opposite. It as the convergence is decreasing, moving in the same direction. So part of the differences between Queen Charlotte and Pusiger, I think, are related to how much convergence can accumulate in the time period. The crust at Queen Charlotte is being generated somewhere south of Haida Gwaii. As it's translating, there's a really like kind of a hard limit on how much it can mature, maybe with regards to subduction initiation. So I think it's also very uncertain, like what the future evolution might be. But yeah, that might not really answer your question well. But I think I haven't really thought about how the connection to the Alpine fault influences what the deformation at Pusiger. But I think it is it's a good thought for sure. I think I'd have to explore some more.
Yeah, thank you.
Hi, thank you. So I guess I'm going to ask kind of a related question, like how do you think any connection, or is there any connection with the Cascadia subduction zone in the south is related to this? And like, do you see differences as you go further away from Cascadia and like perhaps the development of like how well developed the subduction zone is, or like, you know, how connected is it to Cascadia?
I don't think the distance to Cascadia has too much of an impact on the development, but maybe related to Cascadia is more the sort of details of the Explorer triple junction region. Oh man, I didn't mean to do that. Okay, well, sorry people on Zoom. I was going to try to show you a map. So between Queen Charlotte and Cascadia is the Explorer microplate and the Queen Charlotte triple junction area. And so this sort of whole region is very unstable right now, and it's been actively evolving. So this dashed line you can sort of see is called the Revere-Delwood fault. And people have thought that potentially that fault is sort of taking over the strike slip motion from the southernmost Queen Charlotte. So the evolution of Explorer plate is probably influenced partially by what's happening near Nootka, maybe the northern tip of Cascadia. And that's also sort of influencing what's happening in Queen Charlotte. I guess like really long-term evolution, that this takeover by the RDF probably would make initiation more difficult off of like the southern tip of Haida Gwaii, because there would then be less a smaller region that can actually experience convergence compared to where it is now with the extent of the Queen Charlotte Fault.
Cool, thanks.
Any other questions for Collin?
Related to your feet, to the lithospheric edge of the plates going down, when you do this fit for the terminal edge, you have one which is way above, like with a coefficient of 500, and then you say, oh well, if I decrease that coefficient, I fit the data. What does it mean physically?
Yeah, so the difference in coefficient we think is mostly related to the thickness of sediment on the Pacific plate, right? So this Hasterot curve, this 1D age-derived curve is basically just for sort of bulk oceanic crust. The Queen Charlotte, as we saw in the Pacific plate, has 2 to 3 kilometers of sediment. So I think that would be the first order perturbing the heat flow we'd be observing. I think they're doing a thermal model that accounts for all of this. Maybe it would be a better way to approach it, as we really are just focused on the trend, and the sort of 1 over square root of age trend, the decreasing trend in heat flow was really our main interest there.
You have more BSR on one side than the other. The BSR are linked to hydrothermal circulation, no? So you should have more influence on the hydrothermal circulation on one side than the other also. Could that give that slope, that difference also? Could that give you a slope?
Experience less, yeah. I'm not sure. I'd have to think about it some more. Because I think so, if we think about circulation within the Queen Charlotte Terrace, I don't think I'd expect there to be a significant difference moving along strike within the actual terrace of fluids advecting from the underthrusting up. There should be some less. I think it's something good to explore for sure.
No questions? Yes.
Nice talk. Could you go to slide 55? I think that's a similar question. Yeah, so it seems like you have the theoretical expression that all the curves underestimated what's on the right. Can't see clearly. So does that mean you need a new like theoretical expression to explain your data, or any other thoughts?
I think it just indicates that we should reevaluate. Somebody should redo these thermal models, right? Really, if you sort of think about these curves for each of the different hydrothermal circulation models is really fitting like 2 data points of 2 heat flow data points. So I think reevaluating with all the data maybe would help us to nail it down. I do also think that there's potentially some signal here from either from the Queen Charlotte Fault itself, either if it's much more broad or enhanced fluid flow near it's this quite significant strike slip plate boundary fault. So maybe there's enhanced fluid flow along in that area, and that's sort of raising the temperatures, or potentially it's like a reflection of shear heating along the fault plane. Maybe that's something that some of my co-authors really want to evaluate or explore, is the idea that maybe this is recording some shear heating on the Queen Charlotte Fault itself. But yeah, I think sort of as a first order, suggesting that the thermal models maybe aren't as accurate as they've been portrayed as was our real goal. And then I think this leads open to a lot of future exploration about the region.
More questions for Collin? Well, let's thank Collin one more time. Grad students will be meeting with Collin to go out for lunch, and Emma will be organizing that.